Hello, my name is Rhea Cinco, your first reporter for this Module 5 entitled Internal Flow. And introducing my co-reporters for this topic, we have Ariane, Ate Pinky, John Aaron, Rolando, and Vanessa. So before we go to the lesson proper, let's have first an icebreaker. It's just a simple game that is connected to our topic called 4 Picks 1 Word, where you need to use the following pictures and the jumbled letters below to identify what is being described on each entry within 5 seconds. Are you ready? Let's have the first set of pictures. Number 1. So the answer is fluid. You're correct. Number 2. Very good. It is flow. Number 3. Turbulent flows. You're right. Number 4. It is laminar flow. Great. And the last one is creeping flow. But before we start, let's have first our objectives. When we finish discussing, you should be able to have a deeper understanding of laminar and turbulent flow in pipes and the analysis of fully developed flow. Second, calculate the major and minor losses associated with pipe flow in piping networks and determine the pumping power requirements. Third is understand its different velocity and flow rate. Now that we have hints on what will be discussed today, we have what is fluid and what is flow. So when you heard the term fluid and flow, what comes to your mind? Okay, we all know that a substance in the liquid or gas phase is referred as fluid, while flow is the movement of a liquid or gas in one direction, especially continuously and easily. Now that we learned the meaning of the two words presented earlier, I know that you have now the idea of what is fluid flow. Let us define fluid flow. It is a part of fluid mechanics and deals with fluid dynamics. When we say dynamics, it is the study of forces and motion. It involves the motion of the fluid subjected to unbalanced forces. This motion continues as long as unbalanced forces are applied. But take note, unbalanced forces are those unequal in magnitude that causes change in the state of motion of the object, as shown in the picture below. Moving on, fluid mechanics is actually part of our everyday lives. For example, the hot and cold water that we use in our homes is pumped through pipes. Water in a city is distributed by extensive piping networks, and the blood is carried throughout our bodies by arteries and veins. So these examples are showing that fluid flow in circular and non-circular pipes is commonly encountered in practice. Just for a recall from our learnings from our Module 1.3, where it discusses the classification of fluid. Fluid flow is classified as external and internal depending on whether the fluid is forced to flow over a surface or a conduit. Internal and external flows exhibit very different characteristics. The flow in a pipe or duct is internal flow if the fluid is bounded by solid surfaces, while the flow of an unbounded fluid over a surface such as plate, a wire, or a pipe is external flow. In this lesson, we considered internal flow where the conduit is completely filled with the fluid, and flow is driven primarily by a pressure difference. This should not be confused with open channel flow, where the conduit is partially filled by the fluid and thus the flow is partially bounded by solid surfaces. as in an irrigation ditch, and flow is driven by gravity alone. So looking at this picture here, we have two pipes filled with a fluid flowing left to the right. The inlet of each pipe is denoted by the letter I, while the outlet is denoted by the letter O. In the left scenario, a fluid completely fills the pipe and the pipe is sealed off from the atmosphere. In the right scenario, a liquid partially fills the pipe and there is some atmospheric air above the liquid that comes from the atmosphere. Note that only a liquid can be transported in this matter, as a gas would expand to fill the entire pipe. Liquid or gas flow through pipes or ducts is commonly used in heating and cooling applications and fluid distribution networks. The fluid in such application is usually forced to flow by a fan or pump through a flow section. We pay particular attention to friction, which is directly related to the pressure drop and the head loss during flow through pipes and ducts, and this will be discussed later on. The terms pipe, duct, and conduit are usually used interchangeably for flow sections. Flow sections of circular cross-sections are referred to as pipes, especially when the fluid is liquid, and the flow sections of non-circular cross-section as ducts, especially when the fluid is a gas. Small diameter pipes are usually referred to as tubes. Given this uncertainty, we will use more descriptive phrases such as circular pipe or a rectangular duct whenever necessary to avoid any misunderstandings. You have probably noticed that most fluids, especially liquids, are transported in circular pipes. This is because pipes with a circular cross-sections can withstand large pressure differences between the inside and the outside without undergoing significant distortion, while non-circular pipes are usually used in applications such as the heating and cooling systems of buildings. As shown in this picture, circular pipes can withstand large pressure differences, but non-circular pipes cannot. The fluid velocity in a pipe changes from zero at the surface because of the no-slip condition to a maximum at the pipe center. In the fluid flow, it is convenient to work with an average velocity which remains constant in incompressible flow when the cross-sectional area of the pipe is constant. So this picture shows the average velocity is defined as the average speed through a cross-section. For fully developed laminar pipe flow, average velocity is half of maximum velocity. The value of the average velocity at some streamwise cross-section is determined from the requirement that the conservation of mass principle be satisfied, and that will be shown by this equation, where this m is the mass flow rate, p is the density, ac is the cross-sectional area, and ur is the velocity profile. Then the average velocity for incompressible flow in a circular pipe of radius r can be expressed by this equation. Therefore, when we know the flow rate of the velocity profile, the average velocity can be determined easily. And that's all for my topic from Module 5.1, Introduction to Fluid Flow.
Module 5.2, Laminar Flow and Turbulent Flow. Hi, I am Pinky Dondon and my topic is about the laminar flow. So what is laminar? It's a type of fluid flow that is characterized by smooth streamlines and highly ordered motion. Laminar flow is encountered when highly viscous fluids such as oils flow in small pipes or narrow passages. If you have been around smokers, you probably notice that the cigarette smoke rises in smooth plume for the first centimeters and then starts fluctuating randomly in all directions as it continues to rise. The examples of the laminar flow are oil flow through a thin tube, blood flow, and smoke. Osborne Reynolds, the Irish mathematician and physicist, who discovered that the flow regime depends mainly on the ratio of inertial forces to viscous forces in the fluid. This is his after exhaustive experiments in the 1880s. And the formula is Reynolds number is equal to inertial forces over viscous forces. Note that the Reynolds number is dimensionless quantity. Under the most practical conditions, the flow in a circular pipe is laminar for the Reynolds number less than or equal to 2300. Next is, what is the flow in the entrance region? Consider a fluid entering a circular pipe at a uniform velocity. Because of the no-slip condition, the fluid particles in the layer in contact with the surface of the pipe come to a complete stop. This layer also causes the fluid particles in the adjacent layers to slow down gradually as a result of friction. The region of the flow in which the effects of the viscous shearing forces caused by fluid viscosity are felt is called the velocity boundary layer or the just boundary layer. The hypothetical boundary surface divides the flow in a pipe into two regions. The boundary layer region, in which the viscous effects and the velocity changes are significant, and the irrotational core or flow region, in which the frictional effects are negligible and the velocity remains essentially constant in the radial direction. The region from the pipe inlet to the point at which the boundary layer merges at the center line is called the hydrodynamic entrance region, and the length of this region is called the hydrodynamic entry length. So what is the flow in the entrance region? It is called the hydrodynamically developing flow, since this is the region where the velocity profile develops. The region beyond the entrance region, in which the velocity profile is fully developed and remains unchanged, is called the hydrodynamically fully developed region. This is equivalent to the fully developed flow when the fluid in the pipe is not heated or cold. Thus, the formula is like this. As shown in the figure, the developed average velocity profile is parabolic in laminar flow. As you can see on the arrows, the thickness of this boundary layer increases in the flow direction until the boundary layer reaches the pipe center, thus fills the entire pipe. Entry lengths. In laminar flow, the non-dimensional hydrodynamic entry length is given approximately as LH laminar is approximately equal to 0.05 Reynolds number diameter. So the laminar flow in pipes is the steady, laminar incompressible flow of fluid with constant properties in the fully developed region of a straight circular pipe. Each fluid particle moves at a constant axial velocity along a streamline, and the velocity profile remains unchanged in the flow of direction. So there is no motion in the radial direction, everywhere is zero, no acceleration, and the flow is steady and fully developed. Next is about the pressure drop and the head loss. It is a quantity of interest in the analysis of pipe flow, directly related to the power requirements of the fan or pump to maintain the flow. The pressure drop is expressed as pressure drop is equal to partial pressure less the final pressure is equal to 8 fluid viscosity times length velocity average over r squared is equal to 32 fluid viscosity times length times average velocity over the diameter squared. And a pressure loss, a pressure drop to the viscous effects represents an irreversible pressure loss. Darcy-Weisbach friction, name factor the Frenchman Henry Darcy in 1803 to 1858, and the German Julius Wiesbach in 1806 to 1871. These are the two engineers who provided the greatest contribution in the development. Next is the circular pipe laminar formula. It is friction is equal to 64 fluid viscosity over pressure times diameter velocity average is equal to 64 over Reynolds number. And the formula for the head loss is HL is equal to pressure loss over PG is equal to friction times length over diameter times volume squared average over 2G. Head loss pressure are commonly expressed in terms of the equivalent fluid column height. Pressure losses are commonly expressed. Pressure loss is equal to friction times length over diameter times pressure velocity squared average over 2. So the effects of the gravity on velocity and flow rate in laminar flow, there has no gravity on flow horizontal pipes. Has a significant effect on both the velocity and the flow rate in uphill or downhill pipes. In non-circular pipes, the Reynolds number for flow in this pipe is based on the hydraulic diameter. dH is equal to 4AC over P, where AC is the cross-sectional area of the pipe and P is its weighted perimeter. That's all for my lesson. I hope you have learned something, and thank you for watching. And let's get to know more about the other fluid flow, which is the turbulent flow.
Hello everyone. Today I will be presenting one of the classification of fluid flows, which is the turbulent flow. Turbulence is commonly observed in everyday phenomena such as surfing, fast-flowing river, billowing storm clouds, and even smoke from the chimneys. But first, let's define what is turbulent flow. So, what is turbulent flow? Turbulent flow is the highly disordered fluid motion that typically occurs at high velocities and is characterized by velocity fluctuations. When we say velocity fluctuations, it is the movement of fluids, which is irregular shifting back and forth or up and down of fluids. Turbulent flow is fluid motion characterized by chaotic changes in pressure and flow velocity. It is a flow of low viscosity fluids such as air at high velocities is typically turbulent. It is also caused by excessive kinetic energy in parts of a fluid flow. Another, turbulent flow is a type of flow of fluid in which a fluid travels in irregular path. In this type of flow, the speed of the fluid at a point undergoes changes continuously in both magnitude and direction. Most kinds of fluid flows are turbulent. Examples are flow of air and water. In general terms, in turbulent flow, unsteady vortices appear of many sizes which interact with each other and consequently drag due to friction effects and creases. So, we have here image showing turbulent flow. And now, let's move on to the real-life examples of turbulent flow. So, we have here 8 examples, which is the first is aircraft, second is the smoke, third, rivers, fourth, blood flows in arteries, fifth is the taps, pumps, turbines, 6, flow of fluid under an obstacle, 7, air from fan or air conditioner, and lastly, the car exhaust. So, we have here aircraft, which is the first example. You must have experienced turbulence while traveling on an aeroplane. So, as what the image show here, yes, it show a chaotic movement or turbulent flow. Okay, now let's proceed to example number 2, which is the smoke. The smoke coming out from a cigarette begins with smooth flow, but when it gets mixed, the smoke turns to chaotic. So, as what the image show here, of course, the straight line of smoke is what we call laminar. But the mixed or the messy movement of a smoke is what we call the turbulent. Next example is the reverse. The swirls and the waves observed in a silently flowing river are some of the best examples of turbulent flow in daily life. So, yes, as what we observe from the rivers, it shows swirls and chaotic movement. Next is the blood flows in arteries. The blood flowing in an arteries follows turbulent flow. The curve in an aorta causes the blood flows to get bent, thereby causing the blood cells to get mixed with each other. So, even in our arteries, the flows of blood shows also a turbulent flow. Next is number 5, taps, pumps, turbines. When a tap or a faucet is thoroughly open, the water tends to flow out at a great speed. So, yes, as what the image show here, when we open a faucet, yes, it shows a great speed that shows also a turbulent flow. Next is the flow of fluid under an obstacle. When an obstacle is introduced between the laminar flow of a fluid, the flow gets transformed into turbulent flow. Yes, as what the image show here. After the laminar flow, it goes to turbulent flow. Next is a number 7 example, air from fan or air conditioner. The air coming from a fan or air conditioner does not flow in a straight line. It gets circulated inside the room with the help of rotating blades of the fan. So as what the image show here, yes, it is true that it is not only straight. The produced wind by the electric fan or air conditioner is not only straight, but it circulates. That also produces a turbulent flow. Moving on to the last example of turbulent flow in daily life, which is the car exhaust. The smoke coming out from the exhaust or pipes of the car is classical example of turbulent flow in daily life. So, let's see the image here. As what we can see, yes, the smoke coming out from the exhaust of a car also shows a turbulent flow or chaotic movement. And now, we will be moving on to the characteristics of turbulent flow. Okay, we have here the characteristic of turbulent flow. First, turbulent flow tends to occur at higher velocities, low viscosity, and higher characteristic of linear dimensions. Next, if the Reynolds number is greater than 3,500, the flow is turbulent. Third characteristics is the irregularity. The flow is characterized by the irregular movement of particles of the fluid. Next is the diffusivity. Characteristic responsible for the enhanced mixing and increased rates of mass, momentum, and energy transport. It is a flow called diffusivity. The next is the rationality. Turbulent flow is characterized by a strong three-dimensional vortex generation mechanism. And the last characteristic is dissipation. A dissipation process is a process in which the kinetic energy of the turbulent flow is transformed into internal energy by viscous shear stress. And finally, we will moving on to the Reynolds number for turbulent flow. So, what is a Reynolds number? So, Reynolds number is important dimensionless parameter that identifies the behavior of fluid based on attributes like viscosity or velocity of fluid. It is also a convenient parameter for predicting if a flow condition will be laminar or turbulent. Also, it is defined as the ratio of inertia forces to viscous forces. Reynolds number is mathematically defined as R is equal to V times D times P over U, where V is equal to the average velocity and D pipe internal diameter, P equal to the liquid density, M absolute viscosity, and R is the Reynolds number in a dimensionless value. So, because of the kinematic viscosity, V is equal to U over P, the Reynolds number can also be expressed as R is equal to V times D over small v. For practical purposes, if the Reynolds number is less than 2000, the flow is what we call laminar. At Reynolds number between about 2000 and 4000, the flow is unstable due to the onset of turbulence. These flows are sometimes referred to as transitional flows. And lastly, if the Reynolds number is greater than 3500, the flow is what we call the turbulent flow. That's all, and thank you for listening.
And now let's move on to another topic, which is the turbulent flow in pipes. Most flows encountered in engineering practice are turbulent, and thus it is important to understand how turbulence affects wall shear stress. However, turbulent flow is a complex mechanism dominated by fluctuations, and despite a tremendous amount of work done in this area by researchers, the theory of turbulent flow remains largely undeveloped. Therefore, we must rely on experiments and the empirical or semi-empirical correlation developed for various situations. Turbulent flow is characterized by random and rapid fluctuation of swirling regions of fluid called eddies throughout the flow. This fluctuation provides an additional mechanism for momentum and energy transfer. In laminar flow, fluid particles flow in an orderly manner along path lines, and momentum and energy are transferred across streamlines by molecular diffusion. In turbulent flow, the swirling eddies transport mass, momentum, and energy to other regions of flow much more rapidly than molecular diffusions, greatly enhancing mass, momentum, and heat transfer. As a result, turbulent flow is associated with much higher values of friction, heat transfer, and mass transfer coefficients. Even when the average flow is steady, the eddy motion in turbulent flow causes significant fluctuation in the values of velocity, temperature, pressure, and even density. The first figure shows the variation of instantaneous velocity component Q with the time at a specified location, as can be measured with a hot wire anemometer probe or other sensitive device. It is convenient to think of the turbulent shear stress as consisting of two parts: the laminar component, which accounts for friction between layers in the flow direction, and the turbulent component, which accounts for the friction between fluctuating fluid particles and the fluid body. Then the total shear stress in turbulent flow can be expressed as T total equal to T laminar plus T turbulent. The typical average velocity profile and relative magnitudes of laminar and turbulent components of shear stress for turbulent flow in a pipe are given in the second figure that you can see. Note that although the velocity profile is approximately parabolic in laminar flow, it becomes flatter or fuller in turbulent flow with a sharp drop near the pipe wall. The fullness increases with the Reynolds number and the velocity profile becomes more nearly uniform, leading support to the commonly utilized uniform velocity profile explanation for fully developed turbulent pipe flow. Keep in mind, however, that the flow speed at the wall of centenary pipe is always zero or no slip condition. Consider turbulent flow in horizontal pipe and the upward eddy motion of fluid particles in a layer of lower velocity to an adjacent layer of higher velocity through a differential area as result of the velocity fluctuation V prime as shown in this figure. Pressure drop is also a factor for fluid flow across any length in pipe. There will be a drop of pressure due to frictional shear force acting within the fluids. Therefore, the shear force per unit area due to the eddy motion in fluid particles can be viewed as the instantaneous turbulent shear stress. The turbulent shear stress can be expressed as turbulent shear stress equal to the Reynolds stresses or turbulent stresses. Note that the time average of the product in the fluctuation velocity is not equal to zero, even though the average value of the fluctuating component is zero. In this slide, we can see that turbulent shear stress, total shear stress, and mixing length can be expressed. Eddy motion and those eddy diffusivities are much larger than their molecular counterparts in the core region of turbulent boundary layer. The eddy motion loses its intensity close to the wall and diminishes at the wall because of the no-slip condition. Therefore, the velocity profile is very slowly changing in the core region of a turbulent boundary layer, but very steep in the thin layer adjacent to the wall, resulting in large velocity gradient in the wall surface. So, it is no surprise that the wall shear stress is much larger in turbulent flow than it is in laminar flow that you can see right now. Unlike laminar flow, the expressions for the velocity profile in a turbulent flow are based on both analysis and measurements, and thus they are semi-empirical in nature with constant determined from experimental data. Consider a fully developed turbulent flow in a pipe and let U denote the time average velocity in the actual direction. Turbulent flow along the wall can be considered to consist of four regions characterized by the distance from the wall. The very thin layer next to the wall where viscous effects are dominant is the viscous or laminar or linear or wall sublayer. The velocity profile in this layer is very nearly linear and the flow is streamlined. Next to the viscous sublayer is the buffer layer, in which turbulent effects are becoming significant, but the flow is still dominant by viscous effects. Above the buffer layer is the overlap layer or the transition layer, also called the inertial sublayer, in which the turbulent effects are much more significant, but still not dominant. Above that is the outer or turbulent layer in the remaining part of the flow in which turbulent effects dominate over molecular diffusion or viscous effects. In this slide, we can see the wall shear stress friction velocity, viscous sublayer, thickness of viscous sublayer, and non-dimensionalized variable can be expressed. Here also we can see normalized law of the wall. The logarithmic law and overlap layer can be expressed. As you can see in this figure, it is the comparison of law of the wall and logarithmic law velocity profiles with experimental data for fully developed turbulent flow in a pipe. Here we can see the outer turbulent layer and power law velocity profile can be expressed. Below that, we can see a figure. It is the power law velocity profiles for fully developed turbulent flow in a pipe for different exponents and its comparison with the laminar velocity profile. Note that turbulent velocity profile is fuller than laminar one and it becomes more flat as n and thus the Reynolds number increases. Also note that the power law profile cannot be used to calculate wall shear stress since it gives a velocity gradient of infinity there and it fails to give zero slope at the certain line. But these regions of discrepancy constitute a small portion of flow, and the power law profile gives highly accurate results for turbulent flow through a pipe.
The Modi chart. The experimental results are presented in tabular, graphical, and functional form obtained by curve-fitting experimental data. In 1939, Cyril F. Colebrook combined the available data for transition and turbulent flow in smooth as well as rough pipes in the following implicit relation known as the Colebrook equation. Commercially available pipes differ from those used in the experiment in that the roughness of pipes in the market is not uniform and it is difficult to give a precise description of it. We make the following observation from the Moody chart. For laminar flow, the friction factor decreases with increasing Reynolds number and it is independent of surface roughness. The friction factor is a minimum for a smooth pipe and increases with roughness. The transition region from the laminar to turbulent regime is indicated by the shaded area in the Moody chart. At very large Reynolds numbers, the friction factor curves corresponding to specified relative roughness curves are nearly horizontal. To avoid tedious iterations in head loss, flow rate, and diameter calculations, Swamy and Jain proposed the following relation in 1976 that are accurate within 2% of the Moody chart. These are the types of fluid flow problems. Number 1. Determining the pressure drop or head loss when the pipe length and diameter are given for a specified flow rate. Determining the flow rate when the pipe length and diameter are given for a specified pressure drop. And lastly, determining the pipe diameter when the pipe length and flow rate are given for a specified pressure drop.
Hi everyone, I am May Vanessa Sponga, a BS Science student from SU11, and now I will be discussing the next topic, which is the creeping flow. But before we proceed to the actual discussion, let us first define what is creeping flow. Creeping flow is a type of fluid flow where advective inertial forces are small compared with viscous forces. This is a typical situation in flows where the fluid velocities are very slow, the viscosities are very large, or the length scales of the flow are very small. It is also known as Stokes flow or Reynolds flow. In creeping flow, the Reynolds number is very small, less than 1, such that the inertia effects can be ignored in comparison to the viscous resistance. Creeping flow at 0 Reynolds number is called Stokes flow. And for us to clearly understand creeping flow, let us know what Reynolds number is. So Reynolds number helps us predict flow patterns in different fluid flow situations. In the flow of fluids, a Reynolds number, density, length, velocity, or viscosity describes the relative importance of inertia effects to viscous effects. At low Reynolds numbers, flows tend to be dominated by laminar or sheet-like flow, while at high Reynolds numbers, flows tend to be turbulent. The turbulence results from differences in the fluid speed and direction, which may sometimes intersect or even move counter to the overall direction of the flow or eddy currents. Here are the examples of creeping flow. First is the flow of lava. The viscosity of molten rock is so large that the Reynolds number is small even though the length scales are large. Next is honey. You encounter creeping flow when you pour syrup, a very viscous liquid, on your pancakes, or when you dip a spoon into a jar of honey, also very viscous, to add to your tea. The slow flow of a very viscous liquid like honey is classified as creeping flow. As what you can see on the picture, it shows the flow around a sphere in which the Reynolds number related to the diameter of the sphere d and the velocity of the incoming stream v is less than 1. In this case, the flow is laminar. This type of flow is called creeping flow since the velocity of the moving fluid is very low. In viscous flow, a sphere is affected by a drag force Fd equal to half the velocity of the sphere squared multiplied by the density of the fluid. The cross-sectional area of the sphere A and the drag's coefficient Fd, usually the drag coefficient Cd, is derived experimentally. In the case of creeping flow around the sphere, it is possible to determine the relationship between the drag coefficient and the Reynolds number. That's all. Thank you.